Now we are going to talk about radiation patterns. The antenna not only is connected to the transmitter, but is also sending power to the space that surrounds the antenna. And the antenna does this with a certain directionality. That means that maybe it will be sending the power in different directions with not the same intensity. So the first term that is important is just the radiation pattern. How is defined? It's just the simple representation of the power that is being radiated at a certain distance. And we have some names to talk about. The first case is simple. Assume an antenna that is treating all directions exactly equally. That means that it's sending the same power in all directions. We call this antenna isotropic. Is that what you have here? And if you were to represent this pattern in space, you will see that this is just a simple spherical surface. It will be like a balloon, in a spherical balloon. But if the antenna is sending more power in one direction than in others, or in other words, if it's just taking the power from those directions and sending it in this one, then the pattern becomes directional. And here we have a simple example, which is very frequently used in broadcasting, in radio and television broadcasting. And we call this omnidirectional. It's simple to imagine. Assume you have this spherical surface, which is just a balloon, and you just, in 2 points that are diametrically opposed, you just press them. What happens? But this balloon will just expand, and instead of being in a sphere, will become a donut-sized shape, have a donut shape. And this means that you are not radiating in this direction, and most of the power is going in this direction, in this cone. But all directions around are treated equally well. And thus we call this omnidirectional. If we take the balloon and we just press it from the back, and you just compress it, then the balloon will just expand in this direction. And this is what we have here. This is a directive. And we have here a main lobe, and then we have here small side lobes and a back lobe that is represented here. Excuse me. So this is just the typical pattern for a directive antenna, radio link, or satellite antenna, or satellite receiving, whatever. We have to describe the directionality of the antenna, and we do this with a parameter that is called the directivity. Directivity is assumed to be the value in a certain direction, although we don't say this, but this is always the case. And we represent this normally with the letter D, capital D. Directivity is defined as the ratio of the radiation intensity in a certain direction when you compare with the average value for all directions. This is one way of defining it. For instance, in this case, the directivity in this direction will be the radiation intensity in this direction divided by the value if it were just equally sent to space, which is this one. So if you compare this value with this one, this gives you the directivity in this direction, which here is maximum, but in this direction is 0 because you are not radiating. And here you will see that the directivity is even larger because this value is much larger than this one. So this is just the definition, and for the definition of terms you may go to this standard. It's an IEEE standard that defines all the terms used in communication systems. Remember that directivity is a very important parameter. It's a ratio of power densities in a certain direction compared with the same value you will get if you will radiate it isotropically in all directions. This is one parameter. The second parameter that is being used is called the gain of the antenna in a certain direction. And it's almost the same parameter you had before, but now you don't compare this radiation power with, in certain direction, with the radiated power in all directions, but you do it with the power accepted by the antenna. if it were isotropically radiated. So those two parameters, gain and directivity, only differ. They are different only in the antenna efficiency, which is related to the losses. If there are no losses, then gain and directivity are exactly the same parameter. So we normally talk about gain, and we put here angles to tell you that this value changes with direction for a given antenna. This is for the antenna that is transmitting. But if we now have an antenna that is receiving, then we have to define another parameter. And this is the effective area. Effective area is the parameter that tells you how much power you are taking from the incident wave. And before describing it in technical terms, there's a simple idea. Assume you are in a room, there's a window, and you have sunlight. The sunlight is coming. That means that there's power entering the room, coming through the window. If you know the power density that is arriving to the window, and you multiply this by the area of the window, this will give you a very good approximation of how much power you are accepting. If the window is small, you have a small amount of power inside the room. If you have a large window, then there will be plenty of light and power inside. The effective area is just this parameter. It's the ratio of the available power, or the power that you have at the antenna terminals, divided by the power flash density that is arriving to the antenna, which is a parameter related to the wave. And there's a good thing that simplifies a lot our work as engineers, is that the effective area when the antenna is receiving and the gain when it's transmitted are directly related. And there's a simple ratio that tells you that the effective area and the gain of the antenna, this ratio, is always equal to the square of the wavelength divided by 4 pi. And this is the value for all antenna. That means that if you know the gain of the antenna in a direction, you also know the effective area of that antenna. But remember that gain and effective area include losses on the antenna, on the way we make the antenna. But they do not include impedance or polarization mismatches, and do not depend on the transmitter or the receiver you are connecting the antenna. Those are just parameters directly related to the antenna. There's a third parameter that is useful in linearly polarized antennas, which is the effective length of the antenna. And the effective length of the antenna is just a ratio of the electric field that is incident on the antenna, it relates this incident field, and the open circuit voltage that is being induced in the antenna. And there are quite strong conditions here. One is the antenna has to be linearly polarized, and the second is that the wave that is arriving on the antenna should also be having the same direction of polarization. This is just definition, and here you see that the effective aperture, effective area of the antenna, is directly related to the effective length of the antenna. This is the wave impedance, and this is the distance of the antenna. And also remember that the effective area is related to the gain. So here you can have combination of parameters. If you know the antenna resistance and the effective length, you also know the effective area and the gain. Or if you go to know the effective area and the radiation resistance of the antenna, then you also know the effective length of the antenna. So those are the main parameters that you may find in any set of specifications for any communication systems or for any antenna systems, which are antenna impedance, gain, effective area, and they are all related.